Nielsen. This morning we'll start with a talk which is a joint work of the Royal Technology Institute in Stockholm and Scania, and the presenter will be a colleague of mine from Topsø, Klas Engvall, and he's going to tell us about the role of Alkalil in tar reforming. Please. Thank you.
Well, it's an honor for me to be here and give this presentation. It's actually a presentation supposedly given by Klas Engvall, but we just changed the last name, and I'm taking it and presenting it for him. This is a joint work from KTH, Royal Technology, together with Scania and Topsø, where we look at the influence of biomass-derived impurities on downstream catalysts and performance. Developing a methodology to study these phenomena. But Jens Rostrup Nielsen has been actually an affiliated professor at KTH since 2010, where he works together with Lars Pettersson. I understand they share an interest in arts and science. Jens Rostrup, we all know his contributions to the field of climate technology. A lot of it is focused on steam reforming of hydrocarbons, but also high hydrocarbons, nickel, trace components, carbon formation, the effective carrier systems, and so forth. And a lot of it is summed up in this book with reference therein. This is really an excellent book to start out with to understand these phenomena. But you can have all sorts of speculations on the impact of various conditions and parameters on your system and its response. And during my very short time that I overlapped with Jens Rostrup at Topsø, I was quite, the thing that I remember is you can have all these speculations, but just do the experiment and do the proper experiment to find out what is the influence. And that has certainly influenced the way I think about doing things. Biomass gasification and tar reforming, you take your biomass source, you gasify it to produce syngas, you also have a little bit of sulfur, but some other components. You also form a number of polyaromatic hydrocarbons. You can steam reform them, produce more syngas out of them, and you can send it directly to a gas engine to produce power. But you can also do the classical cleanup, remove the sulfur, purify it. You have a synthesis gas platform, and from there you can go to numerous chemicals. Biomass gasification, typically performed at a temperature of 800 to 900 degrees C, low pressures. The temperature is restricted by the salt, so in the ash, so you don't get too high up in temperature. And this gives rise to a production of higher hydrocarbons in your syngas, C1 to C3, benzene, but also a lot of tars, mainly naphthalene. And also biomass-derived impurities. Now, a way to remove these tars is to steam reform them. This is the component naphthalene that is by far the biggest part of the tars. But the benefits of steam reforming these tars is that you do get the increased syngas production. You convert these tars to a degree that you can allow the gas to be cooled and processed without precipitation and condensation of these tars, which typically is a problem. And you utilize the already present high temperatures at the exit of the gasifier for exegete. There are different ways to do tar reforming. You can either introduce a hot gas filter, removing the dust that also comes with the gas stream. There is so-called clean tar reforming, a low amount of dust. You can operate with pellet-type catalysts. You perform this at the temperatures of 800 to 950 degrees C. So you're essentially isothermal, or at least starting out isothermal with the exit temperature of the gasifier. But you can also do this removing the dust downstream the tar reformer, and this is what we call dusty tar reforming. And there you need monoliths, of course, to let the dust pass through your reactor unhindered. And we have some industrial and demonstration scale experience at Topsø. partly in Skive in Denmark. They're loading here their tar reformer reactor. And we also have experience from Gas Technology Institute in Chicago, in the US. Just very briefly on the scales of these operations. In Skive we operate at about 10,000 cubic meters per hour. The demonstration in Chicago was about 1,200 cubic meters per hour. It's all bubbling fluidized bed under Carbona technology, Skive air blown low pressures, Chicago oxygen blown high pressures, wood pellets. As I said before, in Skive we work with the dusty type, and in Chicago we've been working with the clean version. In Skive we produce combined heat and power by sending the gas to gas engines. And in Chicago we've been focused on the DOE hydrogen project on the tie gas forming, producing gasoline. And in Skive we've been involved basically since they started operation in 2009, but Topsoe became involved in Skive in 2010 since they had tremendous problems getting up and running. And this summer, 2014, it was reformed with Topsoe technology. In Chicago we've been running about 1,200 hours on there and produced a number of gallons of in-spec gasoline. This is the evolving, how the production of power has gone up since we became involved in Skive in 2010. It's been a dramatic increase in their performance, and since the summer after revamp, they're essentially running at full capacity of the gas engines all the time. So that has been a very successful revamp, and it will be interesting to see what the 2015 numbers are, because only part of the revamp is of course included in the 2014 numbers. But what are the impurities in biomass when you do wood gasification, I would say? You do have the alkali metals, you have sulfur, you have chlorine, you have phosphor compounds, you also have ammonia. But all these things and the particular range depends on the feedstock, the gasifier technology, bed material, if you're running dusty or clean, if you have a hot gas filter, and then which temperature this filter is operated at. But impurities in mobile applications, and this is the work we're doing together with Scania, or KTH is performed together with the Topsoe and Scania at KTH. There is increasing legislation and policies moving down in particulate matter and NOx from your diesel after treatment system, and there's likely to come also policies and legislation on CO2 emissions, which means that biodiesel is quite likely to become quite big industry in the future. And this is a picture of a typical Euro 6 downstream system. Here is a Scania engine with an exhaust after treatment system. But the big question then is, what is the impact of this biodiesel on the downstream catalysts? Because biodiesels, they also have similar impurities as you do in biomass gasification. They have alkali metals, alkaline earth, sulfur, phosphorus, and in some cases you may have some zinc present as well. Just a little bit, but I will start mostly, the focus here will be on biomass gasification and tar reforming. There's a lot of things that have been studied prior in the literature. The main feature between the similarities between alkali and sulfur is that you do have a tendency of lowering the intrinsic activity of the catalyst due to the alkali, depending on how you introduce in which amounts. But importantly, alkali increases surface carbon gasification, get a carbon booster coating resistance. This here is these carbon type whiskers that Jens Rostrup has worked quite a bit with. And these grow inside these whiskers grow after the nickel particle, and you get internal pressure in your pellets, and you can completely pulverize your catalyst. So a bit of potassium has proven beneficial, and so has sulfur, but you also do get the activity suppression, and this is all well known in the literature. But the question is, what is the combined effect of all these types of impurities and under realistic conditions? So there's needed some methodology development, how to dose, how to co-dose, and so on. And this is a work we just got accepted in Fuel, a collaboration with KTH, looking on the methodology and some initial results on how to perform these types of experiments. And I'll show you some of these results. The experimental tar reforming setup at KTH, it's fluoride bed, gasifier, biomass gasifier, a hot gas filter. We introduce various salt, alkalis, and other through a aerosol after the filter. And then the gas passes over to the catalytic reactor, and there are various analysis points in your system. Importantly, all these three units are inside its own heat box, so they're all heated to 850 C isothermally. And we've been operating with the Halotopsia nickel magnesium alumina spinel catalyst in their tar reformer. Now why? Let's look at this atomizer or the aerosol generation. You simply have your compressed air, your salt solution, you generate an aerosol, excess liquid goes out, and you have an entrained aerosols in your gas phase with very nice transport properties that you can then deliver to your tar reforming system. Now, why do we choose? Why do they or we choose to work with aerosol and diffusion drying? Under real conditions, salts are present as submicron particles, or it can be in the vapor form depending on the temperature. This aerosol technology has excellent transport properties to your system. There's minimized the losses on wall impaction, deposition, and so forth in your downstream system. And if you operate at temperatures above 800 C and have enough residence time, you get a full, very nice, complete evaporation of your salt now in your gas stream going over your catalyst. You also don't add any additional water to your system because you've done the diffusion drying. The water diffuses, evaporates and diffuses to the dryer, and you don't have particular boiling issues that you can have at the nozzle if you introduce it by the nozzle. So we have a precise control of salts or alkali additions to our system. Now, some initial results. We start off from the fresh catalyst. We add about 11 ppm of potassium chloride. And there are two different cases of sulfur addition. One is the low sulfur addition, 10 ppm, and 3 ppm, which is the higher one. Now I've chosen to denote it with a bold S for the high sulfur coverage. But what we observe is the sulfur uptake and actually saturation in the case when we have a lot of sulfur. Lower sulfur doesn't reach saturation within 500 minutes. But what is very important here and interesting is the fact that the potassium uptake is quite different when you have lower high sulfur. So there is an effect of sulfur on the potassium uptake. And what is not surprising as well is if you start out with a fresh catalyst, initially you have a sintering, fast sintering initially, something that can take place over 200 to 500 hours before this sintering phenomenon is slow. If we look at the catalyst activity, there's nothing suspicious here as well. We all know that sulfur passivates tar reforming activity or hydrocarbon reforming activity. And you get a drop in the naphthalene, you get a drop in the methane conversion time. What is important here is that we have a lot of transients in terms of sintering, but also sulfur uptake and activity of a catalyst. And this is not a model system to look at what is the effect of potassium on top of all this. So what we do, we stabilize the catalyst, we pre-sulfide the catalyst. We know under which conditions we're going to operate during the experiment, and you can buy a Temkin, this Temkin isotherm, or just making sure that the chemical potential of sulfur and the temperature is the same in your pre-sulfidation as in your tests, you have a catalyst where you have sort of taken, already equilibrated with respect to sulfur. Before doing this, before adding the sulfur, you can also accelerate the aging to remove all the transients of catalyst sintering, and that is, you can do a treatment in steam at high temperatures. You need the hydrogen present not to oxidize your catalyst, but this is a way to remove these sintering agents. So now, what is the result? If we start from a pre-treated catalyst, and we did add 11 ppm of potassium chloride as before, what we do observe is this is the sulfur we have here. It stays fixed throughout the experiments. The BET is essentially nearly constant throughout the experiments. This is the pre-treated catalyst, and we observe quite a bit of increase in alkalil. We have learned that you should not treat your catalyst in your system where you've done biomass gasification, because you vaporize or you volatilize all the alkalil that was in the system before, so you have already moved quite a bit of alkalil to the pre-treated catalyst. Irrespective of that, if you operate further on at about 550-40 minutes, you see that we have basically started to also stabilize the potassium level on our catalyst. And the effect on the naphthalene and methane conversion, there's a very small effect, if any, and there's a large uncertainty for these particular measurements of naphthalene conversion as well. So we have a situation where we have the stable BET surface area, the sulfur content on the catalyst is constant from start, and the fact that it stays stable here as well means that the specific nickel surface area is also stabilized. Stabilized catalyst activity. Now we need to move on, work with various different potassium additions and possibly different temperatures. But now we can start looking at what is the potassium influence on the performance of these catalysts. And that is work that is just that is ongoing currently at KTH. If we look at some of the alkali uptake results, there appears to be a slow approach to equilibrium. So we're getting there. With extended studies, we expect to establish what the equilibrium amounts of potassium is on the catalyst under working conditions. And as I discussed before, there's a clear, these two cases are both with 11 ppm, this one is with 6 ppm. What's important here, the difference is there's a difference in the sulfur chemical potential or the sulfur coverage, and that has a clear effect on the potassium uptake. So, to conclude this work here, together with KTH, there's been development of a methodology for looking at surface and gas phase alkali interaction, and this could be any salt. In this case, we'll start out with the alkalis, but you could imagine phosphates and others as well. It includes aging the catalyst, pre-sulfiding it, and then we expose it to realistic producer gas, adding aerosols, and currently ongoing is the effect of establishing various potassium absorption curves and the influence on potassium performance. There's also work at KTH where they will also now start to look at the influence of these various impurities on mobile applications. And this is just a picture of their setup, gases, water, aerosol generator mixture, and then they have 5 parallel reactors in one furnace. And you can look at the aging and the effects of these impurities also on diesel exhaust treatment systems. These are the KTH oil technology collaborators and their funding partners. And with that, I would like to thank you for your attention and open for questions.
Thank you very much, Klas. Questions? Yes, that's one.
You said there was an effect of potassium both on chem absorption on sites and also on promoting carbon growth. Can you talk a little bit about the differences in the extent of deactivation from those two aspects?
Can you repeat the question?
You said that there was an effect of the potassium on carbon growth,
Yeah.
as well as chem absorption of the potassium on two sites. Is that correct?
I can say a few words about, there's a well-known effect of introducing a small amount of potassium to a certain degree where you can get a higher carbon whisker resistance. But what I also discussed was the fact that potassium uptake seems to be dependent on the sulfur chemical potential. We know that sulfur preferentially absorbs on nickel. Alkalil has a tendency of preferentially absorbing on the oxide carrier defects in hydroxyl sites. We also do know that there, in the surface science literature, there is some fairly stable potassium sulfur co-absorption effects on nickel. And if you just look at all these numbers, currently, we cannot tell if the alkali is on the carrier or on the nickel co-absorbed with sulfur. So that will require some further studies. So we don't know the exact location of this alkali. My guess is still it's on the support. Most of it.
Any other questions? But as I understand it, you get your main part of the gas from this atmospheric gasifier, and that's also containing potassium. So how do you know the exact level of potassium?
Yeah, well, if you look at the alkali content of that particular fuel, which is a pine fuel, very low in potassium.
All right.
And you can look at other studies where people have looked at gasification under very similar conditions, and then it's about 0.1 ppm.
Right.
Yeah, and now we're adding 11.
Okay.
So there's a...
But at the same time, you're adding chloride.
Yes.
So you have to assume that chloride doesn't do anything.
That is also an assumption. It means a lot. There's a parametric study
right.
that's needed to do this.
Okay, thank you very much.